Hello everybody, this is Homer White, back again with Chapter 8 of our course. This is Probability and Sampling, and it will come in 5 parts. In this part, we'll remind ourselves of the distinction between parameters and statistics. We'll learn about 5 very basic parameters that occur in elementary statistical analysis situations. They are the mean of a population, the proportion of a population, the difference of 2 means of 2 different populations, the difference of 2 proportions of 2 different populations, the mean of a set of paired differences for one population, and we'll also talk about some tips for distinguishing between these parameters and learning to identify them from some of the basic research questions. Always remember to make sure the necessary packages are loaded. So, a reminder of the distinction between parameters and statistics. A parameter is a number associated with a population. We think of the population as fixed. We also think of it as some fixed time, so that the measurements of the variables on the population are fixed numbers. That makes the parameter that depends on those measurements fixed. It won't depend on chance. However, the population is usually thought of as being rather large, too large for us to take all the measurements ourselves and compute that parameter. So usually the parameter is unknown. A statistic, on the other hand, is a number that we compute from a sample that we've taken from the population. It can be known because we have the sample, but since it depends on the sample, and the sample generally depends on some chance process, the statistic will depend on chance. Now generally we use a statistic to estimate a parameter of some sort. There are some familiar parameter and estimator pairs that you're already intuitively familiar with even before you begin a course in statistics. For example, if you wanted to estimate the mean of a population, denote that by mu, you would probably use the mean of a sample that you've taken from the population, and this sample mean is denoted x with a bar on top, x bar. In a similar way, if you needed to estimate the spread in a population, if you needed to estimate a population standard deviation sigma, let's say, then you might use the sample standard deviation S that we introduced back in Chapter 2 of the course. Many other familiar types of parameter and statistics pairs have the same format, where the estimator is computed from the sample in the very same way that the parameter is computed from the population. So you might estimate the median of a population by simply taking the median of your sample, or estimate the third quartile of your population by taking the third quartile of the sample. Not all estimator and parameter pairs that work this way, but in this course, that's generally what we're going to find. Our hope, of course, is that usually the estimator will somewhat resemble the parameter, won't be too far away from it. As a reminder on the distinction between statistics and parameters, you might want to play again with the Simple Random app. Apply it again to our imaginary population, ImagePop, and look again at the output to the console as you play with the app. Remember, every time you take a sample, there'll be 2 sets of phase stats given. One is phase stats for the sample. Those will give estimators. The other is phase stats for the population, and that's going to say the same every single time because it's phase stats on exactly the same object. The sample estimators will vary, and the population parameters will remain fixed even as you vary the sample. Another pattern that you'll notice if you play with the app again is that if you set the sample size bigger, you'll see that it's quite likely that the estimators will be close to the parameters that they're targeting. So let's get on to the basic 5 parameters that will constitute most of our attention for the rest of the course. These 5 important parameters are the mean of a population, denoted with the Greek letter mu, estimated by the sample mean, x bar, the proportion of a population that possesses a particular characteristic, this is denoted by the letter p, and it'll be estimated by the proportion in our sample that possess that characteristic. We might also be interested in the difference of the means of 2 different populations, and we'll estimate that using a difference of sample means. We might be interested in the difference of two proportions for two populations, and we'll estimate that naturally enough using the difference of sample proportions for samples taken from those respective populations. Finally, we might be interested in the mean of some paired differences for all the items in a population. That's denoted mu subscript d, and we might estimate this with the sample mean of paired differences in our sample. This is denoted d with a bar on top, d bar. So let's take them in turn. One mean. A typical research question where you find yourself interested in one population mean is something like, is the mean height in a MAGPOP more than 66 inches? We want to get some practice in defining precisely the parameter of interest. When we do so, we're going to use the right symbol, and we're going to also define it in words in a precise way. So a good definition might be, let mu equal the mean height of all people in a MAGPOP. Notice that we've carefully referenced the population of interest in our definition of the parameter. The estimator is the sample mean x bar. Because the sample mean is a random variable, it is, after all, a number computed from the sample, and the sample depends on chance. As a random variable, it has an expected value and a standard deviation. The expected value of x bar turns out to be just the mean of the population, mu. Sometimes x bar will be bigger than mu, sometimes it will be less. But if somehow you could take sample after sample after sample and average up the sample means that you get from each sample, in the long run you would get a number extremely close to the population mean, mu. The standard deviation of x bar, remember, is a measure of about how far this random variable could be expected to be from its expected value. And this has an interesting formula. It's the standard deviation sigma of the population divided by the square root of the sample size itself. Notice that the square root of the sample size is in the denominator of the formula for standard deviation. The bigger the sample size, the bigger the square root of n will be, and therefore the smaller the standard deviation. This means that at large sample sizes, we could expect x bar to be closer to mu. Now, I should point out that the formula we just gave for standard deviation is not exactly the correct formula for what happens when you take a sample from a population by simple random sampling. As long as your population is finite, the actual formula is just a tiny bit different from the one that has been indicated here. However, the difference is so small that it's really not worth talking about, as long as the population is large in comparison to the sample size. In practical circumstances, that will be the case. After all, if the population were only a bit larger than the sample, then you might wonder why we didn't bother to go ahead and get information on the entire population anyway. So the approximate formula for standard deviation of x bar that you see here is going to suffice. For all of the other standard deviation formulas that we learn about in this chapter, again, they are only approximations for simple random sampling, but they are very, very close to the actual formulas, and so we will use the approximations without qualm. For one proportion, a typical research question might concern, say, a categorical variable with two values, like the variable math major in a MAGPOP. People either are or are not math majors. And you might ask, are more than 5% of the people in a MAGPOP math majors? So you're interested in one population proportion. The way you might define it is to say, let P be the proportion of all people in a MAGPOP who are math majors. You estimate this with the sample proportion. That is, you look at the number of people in your sample who are math majors and divide by the sample size, getting a sample proportion which we denote P with a little caret or hat on top. The caret or hat in statistics indicates estimation of some sort. Now, P hat is also a random variable. It may not surprise you to learn that its expected value is P, the population parameter that it's trying to estimate. But it's always a surprise to learn the formula for the standard deviation of these random variables. The standard deviation of p hat turns out to be the square root of the population proportion times 1 minus the population proportion divided by the sample size itself. Once again, after you do the algebra, notice that there is a square root of n in the denominator of the fraction for the formula of standard deviation of p hat. So at bigger sample sizes, you can expect p hat to be close to p. How about the difference of two means? A typical research question would be wondering how much taller the guys in a match-pop are, on average, than the gals in a match-pop. Now, to investigate this question, although there is one match-pop population, you really need to subdivide it into two separate populations. You need to look at all of the females in a match-pop and all the males in a match-pop. That's two populations. So the relevant parameters are mu1, the mean height of all males in a match-pop, and mu2, the mean height of all females in a match-pop. Now what we're really interested in is not mu1 and not mu2. In our research question, we were interested in how much taller guys were on average than gals. So we were really interested in the value of mu1 minus mu2. That's actually just one number. If that number is positive, then the guys are taller on average than the gals. If that number is negative, then the guys are shorter on average than the gals. To estimate this parameter, we could take a simple random sample of size n1 from all the guys in a match-pop, compute a sample mean, which we'll call x1 bar, and then take some independent simple random sample of size n2 from all the gals in a match-pop, and again compute the sample mean, but this time call it x2 bar. The estimator will simply be the difference, sample mean for the guys minus sample mean for the gals. Again, unsurprisingly, its expected value is exactly the target parameter, mu1 minus mu2, and the standard deviation is interesting. It involves the standard deviation for the population of guys squared divided by the sample size you're taking from that population, plus the square of the standard deviation of the heights of the gals in a match-pop divided by the sample size for the sample you've taken of the gals. Again, since sample sizes are in the denominators, at large sample sizes, you can expect x1 bar minus x2 bar to be pretty close to mu1 minus mu2. Let's stop for a practice problem here. It's a fill-in-the-blanks problem. If you take a simple random sample of 25 guys and an independent simple random sample of 36 gals from a match-pop, and you compute x1 bar minus x2 bar, then it should turn out to be about something, give or take something else. And we'd like to fill in these two blanks. Now we know that a random variable will turn out to be about its expected value. So we're going to need to find mu1 minus mu2. And we know that the give or take figure for a random variable can be thought of as the standard deviation of that random variable. So we'll need to compute it as well. Now, both of these formulas involve parameters. But since we're in the happy situation of having data for all of a match-pop, we can go ahead and find those parameters. First of all, we already know n1 and n2. They're not parameters, they're just the sample sizes, but let's note them down. 25 are the number of guys that we took, 36 the number of gals. For the other parameters, we might do fave stats on the heights in the population broken down by sex. Now we only want to display the mean and the standard deviation, so we'll use the brackets to do that. And here they are. So we can see the guys in the population are 5.03 inches taller than the gals in the population, and we also have their standard deviations. So the mu1 minus mu2, the expected value of the x1 bar minus the x2 bar, is the 5.03 inches. For the standard deviation of x1 bar minus x2 bar, we simply pull out the formula, And then maybe we can take it to R. Using R as a calculator, we need to take the square root of the standard deviation for the gals, 2.962, square that, divide by the 25 gals. I'm sorry, those are the 25 guys. Here's the standard deviation for the gals divided by the 36 gals, and the result is 0.7766. And so here's how we fill in the blanks. We say that x1 bar minus x2 bar should be about 5.03 inches, the expected value, give or take a standard deviation or two, give or take 0.78 inches or so. How about the difference of two proportions? Here's a typical research question. In a match pop, who's more likely to favor capital punishment, a female or a male? Again, you subdivide a match pop into the two separate populations, all the females and all the males. And again, we need to define our parameters to be clear about what we're talking about. So let's let P1 be the proportion of all females in a match pop who favor capital punishment, and let P2 be the proportion of all males in a match pop who favor capital punishment. So we're interested in P1 minus P2. So for your estimator, you're taking a simple random sample of size, say, N1 from all the gals, and from that sample you compute a sample proportion P1 hat, the proportion of those who favor capital punishment. Take an independent sample, simple random sample of size N2 from all the guys, computing a some sample proportion P2 hat. The estimator is P1 hat minus P2 hat. So we need to simply compute the expected value and the standard deviation using the appropriate formulas. Well, again, it's unsurprising. The expected value of P1 hat minus P2 hat turns out to be exactly the target parameter, and the standard deviation of P1 hat minus P2 hat turns out to be this rather interesting expression. Again, notice that the sample sizes are in the denominators, so at large sample sizes, P1 hat minus P2 hat should be pretty close to its target, P1 minus P2. Now for the mean of differences. Let's switch now and think about, instead of a population, Math 111 survey. So we might have a research question such as, do people at Georgetown College want to be taller than they actually are? Now the population here is not the 71 students that are in Math 111 survey, it's all of Georgetown College. And each person in that population has an actual height and an ideal height. And we're interested in the differences between the ideal height and the actual height for each person. So we define mu d to be the mean difference, ideal height minus actual height, for all people in Georgetown College population. For each person in the population, there's two numbers, the ideal and the actual height, but we reduce it to one number by computing the difference for each person. And it's the mean of those differences that makes mu d. This is going to be an unknown number. We don't have access to the entire Georgetown College population. As for estimating it, it's a simple idea. We just take a simple random sample of size n from the population. We can record the ideal and actual height for each person in the sample. We can compute the difference, ideal minus actual, for each person, and then compute the mean of these differences. This is written d bar, somewhat an analogy with x bar for a one sample mean. Again, no surprises for the expected value. The expected value of d bar is exactly mu d. The standard deviation of d bar is the standard deviation of the differences for the population of all Georgetown College students divided by the square root of the sample size. Again, in this case, as in most real cases, we don't have access to the entire population, so we're not going to be able to just compute mu d and sigma sub d directly. We won't know the exact values of the expected value and the standard deviation for this particular estimator d bar. Now, I'd like to talk about some tips for identifying the parameters of interest that emerge from various research questions. One tip is to pay attention to keywords. For example, look at the research question, on average, do the people in a MAGPOP make more than $38,000 per year? The term on average often indicates interest in a mean. Here, a natural choice for the parameter of interest would be a 1 mean. Let mu be the mean income of all people in a MAGPOP. And then your research question boils down to, is mu bigger than 38,000? Another example of using keywords. Suppose your research question is, do a majority of people in a MAGPOP favor capital punishment? When you see words like majority or minority, they often indicate an interest in a population proportion of some sort. So, for example, you might let the parameter be P, the proportion of all people in a MAGPOP who favor capital punishment. Then, asking if a majority of people in a MAGPOP favor capital punishment is the same as asking if P is bigger than 0.5, 50%. Another really important tip is to use variable analysis as much as possible. When the research question involves two variables, as it often does, you want to try to identify each variable. And then, if it's relevant, decide which variable is explanatory and which is the response variable. Also, for each variable involved, classify it. Is it a factor variable? Is it a numerical variable? Also, for each factor variable that you find, count how many levels, how many possible values that factor variable has. I cannot stress enough the importance and helpfulness of variable analysis. So let me give you some examples of how helpful this is. Say you've got a research question. On average, who drives faster at Georgetown College, a guy or a gal? Let's do our variable analysis. One of the variables of interest appears to be sex. Another variable of interest appears to be the variable fastest speed ever driven. Now, sex, we could think of that as the explanatory variable. We think one's sex might be what makes a difference in how fast one chooses to drive. Now, sex is a factor, and its two levels, its two possible values, are male and female. The variable fastest is our response variable, and that's a numerical variable, various possible speeds. Now, in a situation where your explanatory variable is a factor with two values, and the response variable is numerical, then quite likely you're going to be interested in the difference of two population means. Also in this research question, the term average occurred, and that further supports the idea of being interested in means. So we might define mu1 to be the mean fastest speed ever driven for all males at Georgetown College, and mu2 to be the mean fastest speed ever driven for all females at Georgetown College. Notice two parameters, one for each of the two possible values of sex. And we're interested in mu1 minus mu2. That should be a minus. Another example of variable analysis. Take the research question, at Georgetown College, who's more likely to believe in love at first sight, a guy or a gal? So the explanatory variable in this research question is sex. We think sex might make a difference in how you feel about love at first sight. Again, it's a factor with two values, male and female. The other variable is that variable love first in the data frame Math 111 survey. So that's the response variable, and remember that it has two possible values. No, I don't believe in love at first sight, and yes, I do. Now, if you're in a situation where the explanatory variable is a factor with two values, and the response variable is a factor with two values, then probably you're going to be interested in the difference of two population proportions. I'd also point out that proportions can stand for probabilities. For example, the proportion 0.48 can stand for a 48% chance of something happening. This research question used the keyword likely, and so that gives further evidence that we're probably interested in some proportions in this population. We seem to be interested in the difference of some probabilities. So we might define P1 to be the proportion of all males at Georgetown College who believe in love at first sight. and P2 to be the proportion of all females at Georgetown College who believe in love at first sight. P1 and P2 can be thought of as the chances for a male or a female to believe in love at first sight. And so when we're interested in who's more likely to believe in love at first sight, we're interested in P1 minus P2. Again, this should be a minus, not an equals. P1 minus P2. Here's a third example of variable analysis. On average, do people at Georgetown College want to be taller than they actually are? So there's two variables in this question. One is height in the data frame Math 111 survey. That's a numerical variable. And the other is ideal height. That's also a numerical variable. The explanatory and response distinction does not apply here. Neither one of those variables is really explanatory. What we've got here is repeated measures. There's two measurements taken on each person. What's your height? What's your ideal height? When you're in a repeated measures situation or in a matched pairs situation, and both variables are numerical, then you're probably interested in the mean of differences when it comes to a population. And that's what's going on here. We're interested in mu d, the mean difference, ideal height minus actual height, for all students at Georgetown College. Now, I should warn you that not everything fits into one of the 5 basic parameters that we've been studying in this video lecture. There are quite a few interesting research questions that just don't fall into one of these 5 categories. For example, how about the research question, at Georgetown College, do males and females differ in their seating preferences? Here the explanatory variable is sex, and it's a factor with 2 values, male and female. The response variable is seat. It's a factor, has 3 values, front, middle, and back. Now, we've dealt with situations where the explanatory is a factor with 2 values, and the response is a factor with 2 values. But here the response has 3 or more values. So I really can't think of the response directly in terms of proportions. So I can't cast my question as a question about the difference between 2 proportions. If I wanted to reduce the variable seat so that it was only 2 values, for example, if I were interested in people sitting at the front versus not sitting at the front, that's 2 values, then I could think of it in terms of a P1 minus P2 type of question. But unless I have a special reason for reducing the variable like that, I don't have a P1 minus P2 research question. However, both of the variables are factors, so I can still study this research question with techniques that we've already learned, with descriptive techniques like two-way tables, or inferential techniques like the chi-square test. Here's another example of non-fit. At Georgetown College, who has the highest GPA on average? A person who prefers to sit in the back, the middle, or the front? Here the explanatory variable is seat. We're wondering if where you prefer to sit makes a difference in your GPA. And it's a factor with 3 values, front, middle, and back. The response variable is GPA, and it's numerical. So this time the explanatory variable is a factor with 3 or more values. So I'm not going to be able to be in a mu1 minus mu2 situation. You might think of us being interested in means, and since there are means present in the problem, but there's 3 means. There's the mu sub f, the mean GPA of all students who prefer the front. There's a mu sub m, the mean GPA of all students at Georgetown College who prefer the middle. And a mu sub b, the mean GPA of all students at Georgetown College who prefer the back. And when you're wondering whether seating preference makes a difference on average in one's GPA, you're wondering if all 3 of those means are the same or not. But you see it's a difference about 3 population means. It's not a question about the difference between any 2 of those means. If I wanted to squeeze this into a mu1 minus mu2 type of situation, then I would need to reduce my factor variable down to having just 2 values. Say, everybody who sits in front versus not sitting at the front. But unless I have a special reason to do that, I should just leave it as it is, an interesting research question that doesn't fit into our Big Five parameter framework. It can be analyzed, but by techniques that we don't learn in this course. Thank you for listening.